So, how's your experiment?
Freshwater crabs require specificity and attention to details as much as any other pet. Unlike aquarium fishes in tanks, owners may often neglect to provide aquarium crabs with optimal temperature, humidity, and wavelengths of light, which is better suited to the crab's natural living conditions. Most may not know this, but abiotic factors affect a crab's well-being and are crucial to its survival.
Particularly, these abiotic factors affect the crab's feeding behaviors. Every living animal has its own set of behaviors which are structured according to their natural habitat. Crabs have their own way of living and responding, which provides them with a sense of security. Thus, these behaviors need to be allowed in an artificial environment as well.
So, how's your experiment?
A tank was used to house each crab. The tank contained equal parts of sand and water. Shrimp pellets were also standardized to be the food of the crabs.
As for the independent variables, 3 table lamps with similar light intensity and varied wavelengths by the use of cellophane paper will be used. The independent variables are the feeding behaviors. The feeding behaviors that are being observed are deposit feeding, scavenging, and suspension feeding. The setup was placed in a dark room to avoid any other light sources and affect our results.
The control experiment was the experiment using white light to be shown on the crabs and observe, record, and analyze their behavior. The crab was first used for the experiment of white light. The results we were collecting were mainly the time the crab spent on equilibration, walking, resting, suspension feeding, deposit feeding, and scavenging. For the experiment using white light, it showed that the time spent resting was the most out of the rest of its activity. For white light, the crab did not eat from the small container in its tank, also known as deposit feeding. Its average equilibration time was about 12 minutes. It was observed that he had been scavenging for more than 1 minute on average, when compared to suspension feeding. He also spent 3 minutes walking around the tank. The crab under the orange light exhibited suspension feeding the most, but the rest was similar.
In this experiment, we used blue light and recorded down the average time taken for equilibration, walking, resting, suspension feeding, deposit feeding, and scavenging. For equilibration time, it spent around 8 minutes, making it the fastest crab to get used to the light that it was exposed to. For resting time, it was spending 26 minutes, close to the amount of time that the crab under orange light has spent on resting too. In terms of the amount of time spent on walking, it was 10 minutes, which is more than the time spent on walking for crab under white light, but lesser than the time the crab under orange light had spent. The time spent on suspension feeding was around 7 minutes, and it is the same as the amount of time as the crab under the white light had spent. Similar to the 2 other crabs, it also did not spend any time on deposit feeding. Lastly, it spent 9 minutes on scavenging, which is more than both the other crabs, respectively, which spent 8 and 7 minutes on scavenging. However, it is essential for us to find out other factors that can affect the results of our experiment. In this case, we have noted that the personality of the crabs may have a significant impact on feeding behavior. Rather than responding optimally across every situation known as behavioral plasticity, some individuals are constrained by consistent differences in behavior over time or across contexts known as annual personality. An individual with bold personality would emerge rapidly from a startle stimulus, while a shy would not, and is correlated with each individual's willingness to engage in risky behavior. Hence, personality can affect feeding behaviors, so we included personality tests for crabs.
The personality test was executed out by poking the crabs with a stick to test for aggressiveness. The crab subjected to blue light was observed to scavenge and suspension feed the most. This may be since crabs have photoreceptors that are maximally sensitive to the light closest or a wavelength closest to that of a blue stimulus. The blue light resulted in higher brightness that enabled the visual system to perform better. Lower wavelengths of light such as blue have a higher frequency, which results in the crabs detecting food particles more easily in both water and land. This was the opposite for the crab in orange light, as orange light has a longer wavelength, leaving the crab to depend on suspension feeding.
Scavenging was evident in the crab under the white light because it is a blend of all the light rays in a light spectrum. It has been stated that the eyes of a crab detect shorter wavelengths of light, particularly blue and ultraviolet, which helps them pick up the morsels of food on the floor. Hence, white light provided enough brightness for the crab to scavenge and recognize food particles in the land.
It was concluded that blue light was the best for crabs in accordance with their results. This was due to the visual system having photoreceptors maximally sensitive to blue light. Hence, blue light is where the crab's visual system performed the best in. Crab owners should resort to blue lights to ensure the well-being of their crabs. This inspires future research work on the crabs. Future researchers can research on the other abiotic factors that affect a crab's well-being. This will help us better treat crabs.